Hold a mug flat on your open palm and turn it in one full circle, keeping it upright, bringing it in under your arm and back around. The mug is exactly where it started. Your arm is twisted up beside your ear. One complete turn was not enough to bring you back, and if you keep going the same way, a second turn untwists you completely. An electron does that. Turn one all the way around, and it does not come back. It comes back as its own opposite, and needs a second full turn before it agrees with itself again. That is a measured fact, confirmed with neutrons in 1975. It is also the last piece of evidence in a 100-year case against the word we use for this property, because electrons are not spinning, have no size to spin with, and face no direction at all. So what exactly is the thing we have been calling spin? By the end of tonight, you will know. Before we start, if you enjoy questioning reality this slowly, a like or subscribe genuinely helps this channel find people. It costs you a moment, and it means the world to me. Now, let's begin. There is a demonstration that happens in undergraduate physics courses every single year, in more or less the same form, in more or less every country, and it never stops working. A lecturer sits on a stool that turns freely. Somebody hands them a bicycle wheel, held by both ends of its axle, and spins the rim up until it is humming. The lecturer sits there holding it, perfectly still, the wheel turning in front of them like a small private planet. Then they tip the wheel over. They rotate it through half a turn, so that the side that was facing left is now facing right, and the moment they do, the stool begins to turn. The lecturer rotates. Nobody pushed them. Their feet are off the floor. There is no motor, no hidden assistant, no trick. They simply turned a spinning object over, and the universe turned them the other way. You are sitting on that stool now, if you like. Feel the weight of the wheel in your hands, the strange stiffness of it, the way it resists being tilted, the way it seems to push back against a movement it has no business objecting to. Tip it over. Feel the world quietly rotate underneath you. No push, no shove, just a slow, inevitable turning, as though something invisible were balancing a ledger you did not know you were on. That ledger is the conservation of angular momentum, and it is one of the most reliable statements in all of physics. The total amount of rotational motion in a closed system does not change. It can be moved around, handed from one object to another, redistributed, hidden, reversed in direction, but the sum stays fixed. When the lecturer flips the wheel's contribution to the total reverses. Something else has to make up the difference, and the only thing available is the lecturer and the stool, so they turn. That is the demonstration. It is clean, it is intuitive, and it is genuinely one of the nicest things you can show a room full of people who are not yet sure whether they like physics. And I want you to hold on to it, because in a moment I am going to show you the same experiment done in a way that should be impossible. Take a small cylinder of soft iron, not magnetized, an ordinary, unremarkable piece of metal, the kind of thing that would sit unnoticed in a drawer. Hang it from a very fine thread so that it can turn freely about its own long axis, and let it settle. Wait until it is completely still. There is nothing spinning anywhere in this setup. No wheel, no motor, no rotation of any kind. Just a piece of iron hanging in the air on a thread, waiting. Now switch on a magnetic field along the length of the cylinder. The cylinder begins to rotate. Not violently. This is a very small effect, and it takes careful equipment to see it at all. In the original experiments, the deflection was a tiny fraction of a degree, read off by bouncing a beam of light from a mirror attached to the thread and measuring where the spot landed on a distant scale. But the rotation is real, it is repeatable, and it is in a definite direction, determined by the direction of the field. Reverse the field, and the cylinder turns the other way. Now think about what the ledger says. Before you switched on the field, the total angular momentum of the cylinder was 0. It was hanging still. After you switched on the field, the cylinder is rotating, which means it now has angular momentum. If nothing else changed, the books do not balance. Angular momentum has appeared out of nowhere, which is not a thing that happens, and if it did happen, it would break one of the deepest laws we have. So something else must have changed. Something inside that piece of iron must have had angular momentum before, pointing in some direction, and must have had it changed by the magnetic field, and the cylinder's rotation is the compensation, exactly the way the lecturer on the stool is the compensation for the flipped wheel. Here is what actually happened inside the metal. The magnetic field magnetized the iron. Magnetizing a ferromagnet means taking the enormous number of electrons in the outer shells of its atoms, whose little magnetic axes were previously pointing in every direction and cancelling one another out, and lining a great many of them up in the same direction. That is all magnetization is, an alignment. And when those electrons align, the total angular momentum they carry along the cylinder's axis changes. The bulk of the cylinder rotates the other way to keep the sum where it was. So the electrons in the iron were acting like the bicycle wheel. Enormous numbers of them, unimaginably small, each carrying its own tiny share of rotational motion, all of it invisible, until you tilt it and let the ledger balance in a way you can see with a mirror and a beam of light. Which sounds fine. It even sounds satisfying. The electrons have this property that we call spin, and spin is angular momentum, and angular momentum obeys the ledger. That is the story most people carry out of school, and it hangs together beautifully. There is only one problem with it. The electrons are not spinning. I do not mean that they are spinning in some subtle way that requires clever mathematics to describe. I do not mean that they are spinning slowly, or spinning about an axis that is hard to define, or spinning in some higher dimension. I mean that the electron is not rotating, that no part of it is going around any other part of it, that there is no motion of any kind involved, and that physicists have known this for almost exactly a century. And yet the ledger still balances. The angular momentum is really there. It is really conserved. It can really be transferred to a cylinder of iron hanging on a thread in a laboratory in Berlin, and that cylinder will really turn, and the amount it turns by can be measured, and it comes out exactly right. That is the situation. There is a quantity in nature that behaves like rotational motion in every respect that we can test, and it belongs to objects that are not rotating and, as far as anyone can determine, have no size to rotate with. We gave that quantity a name in 1925, and the name we gave it was spin, and the name has been causing trouble ever since. It was proposed by 2 graduate students, who were told within days that their idea was impossible, and who tried to withdraw the paper, and were told it was too late. The word survived. The picture did not. What we are left with is a piece of vocabulary that describes something that is not happening, attached to a property that is more precisely measured than almost anything else in science. And that turns out, this is the part I find hardest to get comfortable with, to be the reason that matter has structure at all. Not charge, not mass, this. The reason there is a periodic table is spin. The reason atoms have shells instead of every electron collapsing into the lowest available state is spin. The reason chemistry has rules, the reason carbon behaves differently from neon, the reason your body is made of distinct kinds of stuff rather than an undifferentiated paste, the reason a white dwarf star can hold itself up against its own weight for billions of years, all of it comes back to this property, and the property has no picture. Tonight we are going to find out what it actually is, not what the word suggests, and not the vague gesture that most explanations stop at, but the real answer, which is stranger and cleaner than the story about tiny balls of charge going round. To get there we are going to have to follow the evidence in the order it arrived, because no single experiment forced this on physics. 4 of them did, spread across 30 years, each one individually patchable and collectively impossible to escape. We will watch a magnetic field split a line of light into 3, and then into 6, and then into a pattern nobody could account for. We will watch Einstein himself run this iron cylinder experiment and get the wrong number and publish it as a triumph. We will stand in a cold room in Frankfurt in 1922 while an invisible film of silver develops into 2 black marks that should not be there. And we will find, near the end, that rotating an electron all the way around does not bring it back to where it started. Then and only then will I tell you what spin is. Because the honest answer only makes sense once you have felt every reason why the obvious answer fails. And the obvious answer is about to start failing in Berlin in the spring of 1915 in the hands of the most famous physicist who has ever lived. In the spring of 1915, Albert Einstein spent 3 months doing something he almost never did. He worked in a laboratory, with his hands. Einstein was a theorist by temperament and by reputation. He did his physics in his head and on paper, and the experimental confirmation of his ideas was something other people arranged, usually years later, usually with equipment he had never touched. But in the winter and spring of 1915, at the Imperial Physical Technical Institute in Berlin, he collaborated with a young Dutch physicist named Wanda Johannes de Haas on an actual experiment with actual apparatus, and he cared about it enormously. De Haas was 34 and had married Hendrik Lorentz's daughter, which in the physics of that era was rather like marrying into a royal house. Lorentz was the man who had explained the splitting of spectral lines in magnetic fields, the man whose transformations sat at the heart of Einstein's own special relativity, and the closest thing continental physics had to an elder statesman. De Haas brought Lorentz's laboratory sensibility to Berlin, and Einstein brought a question he had been chewing on for years. The question was, what is magnetism made of? We had known since the 1820s that magnetism and electric current were the same phenomenon seen from different angles. Run a current through a loop of wire and you get a magnetic field that looks exactly like the field of a small bar magnet. André-Marie Ampère had proposed, more than half a century before Einstein was born, that permanent magnets contain enormous numbers of tiny circulating currents, each one a microscopic loop, and that magnetizing a piece of iron simply means lining those loops up so that their fields add instead of cancel. Ampère had no idea what the loops were made of. Nobody did. But the idea had survived, and by 1915 it had a natural, modern interpretation. The loops are electrons going round inside atoms. And here is the beautiful thing Einstein saw. If magnetism comes from circulating charges, then magnetism must come bundled with angular momentum, because a circulating charge is a moving mass going in a circle, and a moving mass going in a circle has rotational motion. The two properties would be welded together. You would not be able to change one without changing the other, and that means you could test the idea mechanically, with a piece of string. This is the experiment from the last part, a cylinder of unmagnetized iron, suspended from a torsion fiber inside a coil, hanging still. Switch on the field along the axis, magnetize the iron, and if Ampère's circulating currents are real, the alignment of those currents changes the total angular momentum inside the metal, and the cylinder must rotate to compensate. It rotated. Einstein announced the result to the German Physical Society on the 7th of May, 1915. He wrote that experiments performed jointly over the preceding 3 months had, in his opinion, firmly established the existence of Ampère's molecular currents. He was delighted. He thought he had reached down into the interior of a piece of metal and demonstrated, mechanically, what magnetism is. He had done something better than that, and he did not know it. He had performed the first experiment in history on electron spin, and he had got the number wrong. The number in question is called the gyromagnetic ratio. It is simply the ratio between how much magnetic moment a thing has and how much angular momentum it carries. how much magnetism you get per unit of rotation. It is usually expressed through a dimensionless factor written as a lowercase g, and the point of g is that its value tells you what kind of thing is doing the magnetizing. If the magnetism comes from ordinary orbital motion, electrons going round nuclei, charges circulating in loops, exactly the ampere picture, then G comes out equal to 1. That is not a guess or an approximation. It follows directly from the definitions. Charge going round in a circle, mass going round in the same circle, ratio fixed, G equals 1. Einstein and de Haas measured a value consistent with 1. Of course they did. It was what they expected. It was what the theory predicted, and their apparatus had large uncertainties. The rotation is minuscule. The suspension is sensitive to every vibration in a building in the middle of Berlin during a war, and the correct way to read the result was to bounce light off a mirror and watch a spot of light creep along a scale. When you are looking for a specific number, and your equipment can produce a range of numbers, the number you are looking for has a way of turning up. Over the following decade, other people repeated it more carefully. Emil Beck in 1919, Chattock and Bates, Sucksmith and Bates through the 1920s. Samuel Barnett, on the other side of the Atlantic, ran the experiment backwards. Instead of magnetizing iron and watching it turn, he spun an unmagnetized iron rod at high speed and found that the act of spinning it magnetized it. Same relationship, opposite direction, independent apparatus. And they all found the same thing. The gyromagnetic factor for iron is not 1. It is close to 2. That factor of 2 is one of the most consequential errors in the history of physics, and it sat there, unexplained and unexplainable, for 13 years. Think about what it means. Whatever is carrying the magnetism inside a piece of iron produces about twice as much magnetic field per unit of angular momentum as any orbiting charge possibly can. It is getting double value. If you insist on picturing it as a little loop of current, you have to say that the loop is somehow generating twice the magnetism it is entitled to, given how much it is turning. There is no way to arrange charge and mass in a rotating object that does this. None. You can make G smaller than 1 by putting the mass further out than the charge, and you can make it larger by putting the charge further out than the mass. But you cannot get to 2 with any distribution that also holds together and also gives the right total charge. People called it the gyromagnetic anomaly, which is the polite scientific way of saying, we have a number and we do not know why. It is worth being precise about the measured value, because the precision is part of the story. In iron, the experimentally determined factor comes out at around 1.9 rather than a clean 2, and for a long time that untidiness looked like sloppy technique. It is not. We now know that in iron roughly 95% of the magnetization comes from the property we are chasing tonight, and the remaining 5% or so does come from genuine orbital motion of electrons around nuclei. Real circulation, real ampere currents, exactly as Einstein imagined. So the measured number is a blend. It is 95% of a thing with G equal to 2, mixed with 5% of a thing with G equal to 1, and the blend lands a little short of 2. Einstein was not entirely wrong. He was 5% right, and he had found the 95% without recognizing it. The experiment did not stop in 1915 either. A version of it is still being run today, in laboratories that magnetize and demagnetize thin metal films with laser pulses lasting a few quadrillionths of a second. When you destroy the magnetic order in a film that fast, the angular momentum that was stored in the alignment has to go somewhere, and it has nowhere to go except into the physical lattice of atoms. Within about a trillionth of a second, the film's atoms are shaking with the rotational motion that the magnetism used to hold. It is the Einstein-de Haas effect, run a billion times faster, watching angular momentum leave one form and arrive in another in real time. The ledger from the first part of this episode is still balancing, still to the last decimal place, in equipment Einstein could not have imagined. And the reason I want you to sit with this, rather than rushing past it, is that this is the first crack. Everything else in tonight's story is a widening of this crack. In 1915, there was no reason to think that anything was wrong with the picture of electrons orbiting nuclei like tiny planets. Bohr's model of the atom was 4 years old and doing well. Quantum mechanics as we know it did not exist and would not for another decade. There was one small numerical discrepancy in a difficult experiment measuring a tiny rotation, and the obvious thing to assume was that somebody had made a mistake. Nobody had made a mistake. The universe was quietly reporting that the magnetism in a bar of iron does not come from anything going round. There is something almost tender about Einstein's part in this. He walked into the laboratory to prove that magnetism is motion, and the experiment answered him honestly, and he read the answer as agreement because that is what he was listening for. It would take another 10 years and a great deal of embarrassment before anyone understood that the iron had been telling him the opposite. And when the explanation finally arrived, in 1928, it did not come from a better version of the experiment. It came from a young man in Cambridge writing down an equation for entirely unrelated reasons and discovering that the number 2 fell out of it, whether he wanted it or not. But we are a long way from Cambridge. Before we get there, we need to look at light. Because while Einstein was hanging iron cylinders on threads in Berlin, the same missing property was writing itself, over and over, in the colors coming out of hot gas. 19 years before Einstein hung his iron cylinder on a thread, a young Dutch physicist named Peter Zeeman did something he had been explicitly told not to do. Zeeman was working in Leiden, in Hendrik Lorentz's department, and he had become interested in an old question. Michael Faraday, in the last months of his working life, had tried to find out whether a magnetic field could change the light emitted by a flame. He had failed. He did not have the instruments. The question had been left there, more or less untouched, for decades, and Zeeman's supervisor considered it a dead end and a waste of laboratory time. Zeeman did it anyway. He put a flame of burning sodium between the poles of a large electromagnet, and he looked at the light coming out of it through a diffraction grating, which spreads light into its constituent colors far more finely than a prism. Sodium, when you burn it, produces a very particular yellow. It is the yellow of old street lamps, the sodium vapor lights that used to make city roads look like the inside of a photograph. That yellow is not a broad band of color. It is 2 extremely narrow lines, at very specific wavelengths, and they are narrow because they correspond to electrons in sodium atoms making one precise jump between 2 precise energy levels and releasing the difference as light. The color of a spectral line is a direct readout of an energy gap inside an atom. With the magnet off, Zeeman saw the lines exactly where they should be. With the magnet on, they got wider. That was all he saw at first, a broadening, not a splitting. His field was not strong enough, and his grating was not fine enough, but it was enough to know that something real was happening. And when he improved the apparatus, he saw what the broadening actually was. The line had not smeared, it had split. Where there had been 1 line, there were now 3. The original wavelength still in the middle, and 2 new ones on either side of it, equally spaced. The year was 1896. 6 years later, in 1902, Zeeman and Lorentz shared the Nobel Prize in Physics for the discovery and its explanation, the second Nobel Prize in Physics ever awarded, and one of the fastest turnarounds from result to prize in the history of the award. And the explanation was Lorentz's, and it was completely classical, and it worked. Here is the picture Lorentz used. Treat the electron inside the atom as a small ball of negative charge moving in a circular orbit. That is a charge going round a loop, which is a current in a loop, which is a magnetic dipole, a tiny bar magnet, with a north end and a south end, produced not by any material magnetism, but simply by the fact that charge is circulating. Now put that tiny bar magnet inside a big external magnetic field. A magnet in a field has an energy that depends on its orientation. Point it along the field, and its energy is lowered. Point it against the field, and its energy is raised. Point it sideways, and it sits in between. So the same electron, doing the same orbit, has slightly different energy, depending on which way its orbital loop is tilted relative to the external field. And energy differences are what spectral lines are made of. If the upper level of a transition splits into three slightly different energies, then the light coming out of that transition splits into three slightly different wavelengths. One line becomes three lines, exactly as observed. This is a genuinely lovely piece of physics, and I want to give it its due before I take it away from you. Lorentz did not have quantum mechanics. He did not have a correct model of the atom. Rutherford would not discover the nucleus for another 15 years. He had classical electromagnetism and a willingness to take seriously the idea that light comes from moving charges inside matter, and with those tools alone, he explained a brand new experimental effect quantitatively. The spacing of the split lines that his theory predicted matched the spacing that Zeeman measured. More than that, the effect told you something you could not otherwise get. From the size of the splitting, Lorentz could extract the ratio of the charge to the mass of whatever was moving inside the atom. He got a number. It was enormous. The thing doing the emitting had a charge-to-mass ratio thousands of times bigger than any known ion, which meant it was either very highly charged or extremely light. And it was negative. This was a year before J.J. Thomson identified the electron in cathode rays. Zeeman's split lines, read through Lorentz's equations, were among the first solid indications that atoms contain a light, negatively charged, mobile constituent. Physicists were, in effect, weighing the electron by looking at yellow light from a flame and noticing that a magnet made it wider. So, by the turn of the century, here is where we stand. Atoms contain small negative charges. Those charges move. Their motion generates magnetism. A magnetic field interacts with that magnetism, shifting energy levels in a way that depends on orientation, and the shifts show up in light as a line becoming three lines. Everything is consistent. Everything is classical. The universe, in this corner of it, is behaving exactly like a collection of extremely small, extremely ordinary objects doing extremely ordinary things. And the effect turned out to be useful far beyond the laboratory bench where it was found. In 1908, George Ellery Hale pointed a spectrograph at a sunspot and looked for Zeeman splitting in the lines coming out of it. He found it. The lines were split, and from the size of the splitting, he could read off the strength of the magnetic field inside the spot, a few tenths of a Tesla, which is roughly the strength of a good refrigerator magnet, spread across a region larger than the Earth. Nobody had ever measured a magnetic field on another body before. Hale did it from 93 million miles away, by measuring how far apart two lines of light had moved. That technique is still the backbone of stellar magnetism today. Every map of a magnetic field on a distant star traces back to Zeeman, noticing that a flame got slightly wider. There is also a limit to the effect that is worth knowing about, because it will come back. If you keep increasing the external magnetic field, the splitting pattern eventually changes character. The complicated arrangements simplify and collapse back toward the tidy three-line picture. This is called the Paschen-Back effect. And what is happening is that the external field has become strong enough to overwhelm the internal coupling between the different sources of magnetism inside the atom, and to grab each of them separately. In a weak field, they act as a team. In a strong field, they are torn apart, and each responds on its own. The fact that there is an internal coupling at all between two different things inside the atom that can be pulled apart by a strong enough field is a clue sitting in plain sight decades before anybody read it. I want you to notice how comfortable that feels. That comfort is the thing this episode is going to spend the next hour and a half taking apart, and it is worth registering that it was earned honestly. The classical picture was not naive. It was not a failure of imagination. It was a theory that made a quantitative prediction, was tested, and passed. There is even a name for this well-behaved version of the effect. Physicists call it the normal Zeeman effect. One line into three, spacing as predicted, everything accounted for. The word normal is doing an enormous amount of work in that phrase, and it is a lie. Because the normal Zeeman effect, it turns out, is the rare case. It happens only in a specific and rather special class of atoms, for a reason nobody would understand for another 30 years. In most atoms, including, as it happens in sodium, the very element Zeeman started with, turning up the resolution reveals something else entirely. Not 3 lines, 4 or 6, with spacings that Lorentz's beautiful classical calculation cannot produce, no matter how you adjust it. They called that one the anomalous Zeeman effect, and it broke atomic physics for 25 years. There is a story about Wolfgang Pauli that physicists still tell, and like most stories that survive 100 years, it is repeated because it is exactly true to character. Pauli was in Copenhagen in the early 1920s, walking through the streets, looking miserable. A colleague, the version I like best has it as a friend who did not know him well, stopped him and asked why he looked so unhappy. Pauli's answer was, "How can one look happy when he is thinking about the anomalous Zeeman effect?" He was not being dramatic. This problem had a grip on the best minds in physics for the better part of 2 decades, and it did so because it was not a large, obvious philosophical crisis. It was a small, precise, arithmetic humiliation. Here is what the anomaly is. Take the beautiful classical picture from the last part. Electrons orbiting, orbits acting as tiny current loops, the loops having orientations, the orientations having energies, one spectral line becoming 3. That picture makes a very specific prediction about how many lines you get and how far apart they are, and the prediction is rigid. There are no free parameters to adjust. Given the strength of the field, the splitting is what it is. In many atoms, that prediction fails. The sodium doublet, the 2 yellow lines Zeeman started with, is the standard example. Put sodium in a magnetic field, and one of those lines splits into 4 components, and the other splits into 6, not 3. And the spacings between the components are not the spacings the theory gives. They are fractions of it, and they are different fractions for the 2 lines. Similar patterns turned up everywhere once people looked. Some transitions gave 9 lines, some gave 12. The patterns were reproducible, they were beautiful in their own way. Physicists spent years cataloguing them and drawing them out on paper as little arrangements of ticks, and there was no theory on Earth that could produce them from electrons going round nuclei. For a while, the response was to build patches. Alfred Landé, in 1921, did something that in hindsight is almost eerie. He looked at the catalogue of patterns and worked backwards, treating the splittings as data and asking what formula would generate them. He found one. It involves a factor now called the Landé G factor, and if you feed in a set of quantum numbers labeling the atom's state, it spits out the correct splitting for essentially every case people had measured. The formula worked. Landé had no idea why. It was a curve fit, an equation extracted from a table of numbers by pattern recognition and cleverness, with no physical mechanism underneath it at all. And it was the best thing anybody had. But there was something disturbing hiding inside it. To make the formula produce the observed patterns, the quantum numbers going into it had to include half integers, not 1, 2, 3, but 1/2, 3 halves, 5 halves. That was a scandal. Everything in the old quantum theory was built on whole numbers. Bohr's atom had electrons in orbits labeled 1, 2, 3. Angular momentum came in whole units of the fundamental quantum. A half was not merely unexpected, it was a violation of the entire architecture. And various people spent real effort trying to reformulate the whole scheme to make the halves go away. They would not go away. They kept coming back, in more and more places, like a stain that keeps rising through fresh paint. And then, in 1925, Pauli did something characteristically ruthless. He stopped trying to explain the halves, and simply insisted on them. His argument came from a different direction, from the question of why atoms have shell structure at all. If electrons all sought the lowest available energy, every electron in every atom would fall into the innermost level and stay there, and every element would behave more or less the same, and there would be no chemistry. Something stops them. Pauli worked out what the rule had to be. No two electrons in an atom can share the same complete set of quantum numbers. That is the exclusion principle, and he stated it in 1925, and it earned him the Nobel Prize in Physics 20 years later, nominated by Einstein. But to make the counting come out right, to get the right number of electrons in each shell, which is to say, to get the right shape for the periodic table, he needed one more quantum number than anybody had. 3 numbers described where an electron was and how it was moving. He needed a 4th, and the 4th one could take exactly 2 values. 2, not 3, not a continuum, not a whole number of orientations. 2. And with that 4th 2-valued number in place, the counting suddenly worked. The innermost shell of an atom holds 2 electrons. The next holds 8. The one after that holds 18. Those numbers had been known from chemistry for decades and had the feel of arbitrary facts about the world, the sort of thing you memorize rather than understand. With Pauli's rule, they stop being arbitrary. Count the available combinations of the first 3 quantum numbers for each shell, then double the answer because of the 4th, and you get 2, 8, 18, 32, the exact widths of the rows of the periodic table. The shape of that chart on the classroom wall, the one with the awkward step at the top and the long stretched out middle, is a direct drawing of a 2-valued property nobody could describe. There is one more thing this explains, and it closes the loop on the previous part. Remember that the well-behaved version of the Zeeman effect, 1 line into 3, exactly as Lorentz predicted, was called the normal case. It is not the common case. It happens only in atoms where the electrons' contributions of this mysterious 2-valued quantity happen to cancel each other out completely, leaving nothing but orbital motion behind. In those atoms, and only those, the classical calculation is correct, because in those atoms, the thing that breaks the classical calculation has switched itself off. Physicists spent a quarter of a century calling the exception normal and the rule anomalous, which is a very human thing to have done, and a good reminder that the labels a field inherits from its own confusion tend to outlive the confusion. That same mysterious quantity, incidentally, writes itself across the sky in a way nobody in the 1920s could have anticipated. In a hydrogen atom, the electron's 2-valued property can be aligned with or against the proton's own, and the energy difference between those 2 arrangements is tiny. So tiny that the photon released when the atom flips between them has a wavelength of 21 centimeters out in the radio. That transition is so slow that a given atom might wait 10 million years to make it. But there is so much hydrogen in the galaxy that the line blazes across the radio sky, and mapping it is how we know the shape of the Milky Way's spiral arms from inside them. The structure of our own galaxy, as drawn by human beings, is a picture of the alignment of a property with no picture. Now, what Pauli did next tells you everything about him as a physicist. and it is the hinge of this entire episode. He refused to say what it was. He had a property that took two values, that fixed the periodic table, that resolved the half-integers in Landé's formula, and that connected, though this was not yet clear, to the mysterious factor of 2 in Einstein's iron cylinder. Every instinct in physics says, propose a mechanism, say what the thing is, draw the picture. Pauli would not. He described his fourth quantum number, in print, as a classically non-describable two-valuedness. It is an ugly phrase. It is deliberately ugly. It is the phrase of a man who had watched physics get repeatedly humiliated by pictures that felt right, and who had decided that if the mathematics required a property with two values, and the mathematics did not supply a picture, then no picture would be offered. He would name the structure and refuse the story. Listen to what that phrase actually claims, because we are going to come back to it near the end of tonight, and when we do it, is going to sound completely different. Classically non-describable, there is no account of this in the physics of ordinary objects. Two-valuedness, there are exactly two states, and that is the whole of what can be said. At the time it was widely regarded as evasion. Pauli was known for being difficult. This is the man who reportedly said of a colleague's paper that it was not even wrong, and refusing to explain a quantum number he had himself introduced looked to many like stubbornness dressed up as rigor. It was not. It was, as far as I can tell, the single most accurate sentence anybody produced about this subject in the entire 20th century, and it was written by a man who had no idea what he had. So here is the state of physics in the middle of 1925. There is something wrong with the magnetism of iron by a factor of 2. There is something wrong with the splitting of spectral lines that requires half-integers. There is a fourth quantum number that takes two values and holds up the periodic table. Nobody has connected them, nobody has a mechanism for any of them, and the man closest to the center of it has publicly declined to guess, which left an opening for somebody younger and less careful and considerably braver. In January of 1925, a young German physicist named Ralph Kronig arrived in Tübingen with an idea in his pocket. He was barely 21, freshly out of Columbia, traveling through Europe the way promising physicists did in those years, moving between institutes, sitting in on seminars, hoping to be noticed. In Tübingen, he was shown a letter from Pauli describing the fourth quantum number and its two values. Kronig read it, and, within a day or so, had what seemed to him an obvious thought. What if the electron is turning? Not orbiting, turning, rotating about its own axis, the way the Earth rotates while it orbits the Sun. A rotating ball of charge would generate its own magnetic moment, independent of any orbit. That moment would have an orientation which would give the extra energy levels the anomalous Zeeman patterns required. And if the rotation could only be one way or the other, along whatever axis you measured, you would have your two values. Kronig worked out the consequences over the following days. He calculated what the model predicted for the fine structure of hydrogen, the very slight splitting of hydrogen's lines that exists even without an external magnetic field, and he got an answer that was exactly twice as large as the measured value. Then he showed it to Pauli. Pauli's response was withering. Accounts differ on the exact words, but the substance was that the idea was clever and had nothing to do with reality. Kronig, deflated, did not publish. He went on to a long and distinguished career, and he wrote about this episode decades later with a bitterness that had not faded, because in the autumn of the same year, 2 graduate students in Leiden had the same idea and did publish it, and the property has borne their fingerprints ever since. Their names were George Uhlenbeck and Samuel Goudsmit. They were working under Paul Ehrenfest, and they were, by their own later description, not sophisticated enough to know that the idea was impossible. Goudsmit had been immersed in spectroscopy, in the actual tables of line splittings, and Uhlenbeck had a stronger grounding in theory, and between them, they arrived at the picture Kronig had abandoned. The electron has its own angular momentum of 1/2 in the natural quantum unit, and its own magnetic moment, and the two values of Pauli's fourth number are the two possible orientations of that rotation along the measurement axis. They wrote it up as a short note. Ehrenfest read it, said it was either very important or very wrong, and sent it to the journal. Then he suggested they go and talk to Lorentz about it. Lorentz was in his 70s by then, semi-retired, the grand old man of Dutch physics. He listened. He asked for a week, and when they came back, he handed them a sheaf of calculations. Here is what he had done. He had taken the electron's magnetic moment as the experiments required it to be, essentially one Bohr magneton, the natural unit. He had taken the electron size to be the best estimate available at the time, which was the so-called classical electron radius, a length of about 2.8 times 10 to the minus 15 meters, derived by asking how small a ball of charge would have to be for its own electrical self-repulsion to account for the electron's entire mass, and he had asked the simple question, how fast would the surface of that ball have to be moving to produce that much magnetism? The answer was of order 137 times the speed of light. Not close to the speed of light. Not uncomfortably fast. More than 100 times the speed limit of the universe, in a theory built by the man sitting across the table from them, who had personally worked out what happens to objects as they approach that limit. Uhlenbeck later described what happened next. He went to Ehrenfest and said the paper had to be withdrawn, that it was unphysical, that they had been naive, that publishing it would be an embarrassment they would carry for the rest of their careers. Ehrenfest told him it was too late. The paper had already been submitted. It would be printed in 2 weeks. And then he said the thing that people still quote a century later. He told them, "You are both young enough to afford a stupidity." I find that sentence difficult to get past. It is a small act of protection offered by an older man to two frightened students who had just been shown by the most respected physicist in their country that their idea was impossible. He did not tell them they were right. He did not defend the physics. He simply told them that they had permission to be wrong in public, and that being wrong in public would not end them. They published. The paper was 3 pages long, in Naturwissenschaften, in November of 1925. And then came the second factor of 2, the same one Kronig had run into. When you calculated the fine structure of hydrogen with a rotating electron, the answer came out twice as big as observation. Pauli seized on it. He had already dismissed the model once, and here was arithmetic proof. The resolution came the following year, from a British physicist named Llewellyn Thomas, and it is one of my favorite corrections in physics, because it is not a fudge. It is a piece of pure relativity that everybody had simply forgotten to include. An electron in an atom is not moving in a straight line. It is going round, which means it is constantly accelerating, constantly changing the direction of its motion. And in special relativity, when you change reference frames by a boost in one direction and then a boost in another direction, the combination is not equivalent to a single boost. It is equivalent to a boost plus a rotation. Stack up an unbroken sequence of such changes, as an orbiting electron does, and the electron's own frame of reference is being slowly rotated relative to the laboratory, purely as a geometric consequence of moving in a curve at high speed. That rotation is now called Thomas precession, and when you include it, the predicted fine structure is reduced by exactly a factor of 1/2. Which was exactly the discrepancy. The model, with the relativistic correction that nobody had thought to apply, agreed with experiment. And Thomas precession is not some obscure bookkeeping term that lives only inside atoms. It is a real geometric feature of moving in curves at speed, and it has been measured on human-built objects in orbit. A gyroscope carried around the Earth precesses partly because of it. When gravity probe B flew 4 of the roundest objects ever manufactured in polar orbit, and watched their axes drift. Part of what it was measuring was the same effect that fixed Kronig's factor of 2, a rotation that emerges from nothing but the geometry of accelerated motion, with no torque applied, and nothing pushing. Pauli conceded. He accepted the new quantum number as a genuine intrinsic angular momentum. What he never accepted was the picture. And he was right not to, because the speed of light problem never went away. Lorentz's calculation had used the classical electron radius, which is not a real size. It is a scale marker, a number people quote to have something to hold on to. Every subsequent measurement has made the situation worse rather than better. High-energy collisions of electrons and their antimatter partners at the Large Electron-Positron Collider constrained any internal structure to below about 10 to the minus 18 meters, which is 1,000th of the diameter of a proton. Analyses based on the extraordinary agreement between the measured and predicted magnetism of the electron push the effective limit down toward 10 to the minus 22 meters. Shrink the radius, and the required surface speed climbs. There is no size, consistent with any experiment ever performed, at which a rotating electron works. And the modern view, the view the evidence actually supports, is that the electron has no size at all. It is point-like. It has no surface to move. You cannot spin a point. There is nothing at any distance from the center to be carried around, because there is no distance from the center. The angular momentum in the ordinary sense is mass times velocity times radius, and if the radius is 0, then no finite velocity gives you anything but 0. And yet the number is not 0. It is exactly 1/2 of the reduced Planck constant, about 5.27 times 10 to the minus 35 joule seconds, and it never varies, and it can be handed to a cylinder of iron hanging on a thread and made to do mechanical work. So the name arrived attached to a picture that was known to be broken before the ink was dry, and the picture died, and the name lived. That is the entire history of the word spin. 2 students named a property after a mechanism that does not exist, were told immediately that it did not exist, tried to take it back, and were overruled by a journal deadline. We are now 101 years downstream of that deadline, and every physics student on Earth still learns the wrong word first. But nothing so far has actually shown you the impossibility directly. Everything up to this point has been inference, numbers that do not fit, factors of 2, calculations that break. In February of 1922, 3 years before Uhlenbeck and Goudsmit wrote a word, 2 men in Frankfurt had already put the impossibility onto a piece of glass where you could look at it. They just had no idea what they were looking at. Otto Stern had the idea in bed. He said so himself years later, that he conceived the experiment one cold morning in Frankfurt while lying under the covers, reluctant to get up, because the room was freezing and Germany after the war could not reliably supply coal to a physics institute. Some of the best thinking in the history of quantum mechanics happened because a man did not want to put his feet on a cold floor. The idea was this: if atoms really do have magnetic moments with quantized orientations, if the old quantum theory's claim that orientations in space come in discrete allowed values is true, then you ought to be able to see it directly. Not infer it from the spacing of spectral lines. See it, fire atoms through a magnetic field, and let the field sort them by orientation. The physics is straightforward. A magnet sitting in a perfectly uniform field feels a twist, but no net force. Both ends are pulled equally hard in opposite directions, so it turns, but does not move. To make it move, you need a field that is stronger in one place than another. Then the end sitting in the stronger part of the field is pulled harder than the end in the weaker part, and there is a net force, and the size and direction of that force depend on how the magnet is oriented. So, build a magnet with grotesquely uneven poles. One pole shaped into a knife edge, so the field is intense right at its tip. The facing pole grooved and flat, so the field is much weaker there. In the gap between them, the field strength changes enormously over a very short distance. The gradient in the original apparatus was of order 10 Tesla per centimeter, which is a brutal slope for a field to have. Then fire a beam of atoms through the gap and see where they land. Stern chose silver, and the choice turned out to be luckier than he knew. A silver atom has 47 electrons, 46 of which are locked into filled shells where their magnetic contributions cancel out exactly. One electron is left over, alone in the outer shell, and it hands its magnetic moment to the entire atom. So a silver atom is, magnetically speaking, a single electron wearing a very heavy coat. Stern proposed the experiment in 1921. Walther Gerlach, who was better with apparatus, built it and ran it. Now, what should happen? Silver atoms come boiling out of a hot oven. Their magnetic moments point in every direction at random. There is nothing in the oven to line them up. An atom whose moment happens to point straight along the gradient gets the maximum push one way. An atom pointing exactly opposite gets the maximum push the other way. An atom pointing sideways gets no push at all. An atom at some angle in between gets an intermediate push. Since the orientations coming out of the oven are distributed continuously over all possible directions, the deflections should be distributed continuously too. The atoms should arrive at the far end as a smear, a single broadened band, thickest in the middle, where the sideways pointing atoms land, tapering off toward the two extremes. That is what classical physics says, and it is not a subtle prediction. It is the only thing that can happen if magnetic moments can point in arbitrary directions. I want you to be in the room for what they actually found. It is the night of the 7th to the 8th of February, 1922, in the building of the Physikalischer Verein on Robert-Meyer-Straße, in the Bockenheim district of Frankfurt. It is cold, properly cold, the kind of cold where you work in a coat. The apparatus is small, an oven of silver heated until the metal evaporates, a pair of narrow slits to collimate the vapor into a thin beam, the knife-edge magnet, and at the far end, a plate of glass. The whole flight path is only about 3.5 centimeters. Gerlach runs the beam for hours, because the deposit builds up atom by atom, and the rate is agonizingly slow. Then he shuts it down, takes out the plate, and looks at it. There is nothing there. The silver film is a few atoms thick. It is completely transparent. Hours of work, and the plate looks exactly as clean as it did when it went in. He holds it up, turns it toward the light, sees nothing at all, and this is the part of the story that sounds invented, and is not. He breathes on it. Stern smoked cigars. He was paid badly, as junior academics were and are, and so the cigars he bought were cheap, and cheap cigars in 1922 were loaded with sulfur. The air in that room was full of it, and sulfur reacts with silver. It turns bright metallic silver into black silver sulfide, which is the same reaction that tarnishes cutlery in a drawer. The pattern comes up out of the glass in front of him, dark against clear, the way an image rises in a photographic developing tray. It is not a smear. There are two marks, two separate lips of black, curved, arcing apart from one another, and between them, where the overwhelming majority of the atoms should have landed, there is nothing, clean glass. The beam has been cut in half, and the two halves have been thrown to the two extremes, and nothing at all has landed in the middle. The separation between the two spots is about 1/5 of a millimeter. You need a magnifier to be sure of what you are seeing, but once you see it, it does not go away. Stern said afterwards that his poor salary, the salary that forced him to buy bad cigars, had been essential to the discovery. He was joking. He was also entirely serious. Now think about what that plate is saying. Every atom that went through was asked a question by the magnet. How are you oriented relative to this axis? There are infinitely many possible answers to that question in ordinary geometry. A direction in three-dimensional space is a continuous thing. You can point a compass needle anywhere, and every single atom answered with one of two values. Not two clusters with a spread, two spots, sharply defined, with the exact deflections corresponding to full alignment and full anti-alignment, and nothing whatsoever in between. Half the atoms one way, half the other, and not one atom out of the enormous number in that beam giving any other answer. This is what physicists mean by space quantization, and it is the first time in history that anybody saw it directly. Not the energy of a thing coming in discrete lumps, that was already familiar from spectral lines. A direction coming in discrete lumps. The angle itself quantized. The luck in this experiment is almost embarrassing when you lay it out. Stern and Gerlach were testing the Bohr-Sommerfeld theory, which predicted that orbital angular momentum would be quantized in a way that should have given 3 spots for the case they thought they were studying. They got 2. They took the 2 spots as confirmation of a theory that was in fact wrong, and the reason they got such a beautifully clean result was that silver's outer electron has no orbital angular momentum at all. So the only thing in the apparatus was the property nobody had named yet, and it has exactly 2 states. Almost every element of that sentence is an accident. Wrong theory, right apparatus, an element chosen for practical reasons that happened to isolate exactly the effect that mattered, and a cheap cigar to develop the plate. The experiment nearly did not happen at all. Germany's hyperinflation was destroying research budgets, and the funding to keep the apparatus running came through at the last moment, partly through Einstein's efforts, and partly from a check sent by Henry Goldman, a banker in New York who had never met either of them. Stern received the Nobel Prize in 1943. Gerlach never did. Stern was nominated for it 82 times, more than almost anyone in the prize's history. It is worth saying plainly that none of this depended on silver. If you run the same experiment with a beam of plain hydrogen atoms in their ground state, 1 proton, 1 electron, nothing else, you get the same 2 spots. That was done, and it settled any suspicion that the result was some quirk of a heavy atom with 47 electrons in it. The 2-valuedness belongs to the electron. Everything else in the apparatus is scaffolding. And the experiment did not stay a historical curiosity. The same principle, sort particles by their magnetic orientation, then look at where they land, is now routine. Physicists perform the equivalent measurement on single trapped ions, on ultra-cold neutral atoms held in laser light, and on individual electrons parked in solid-state devices. In some laboratories, it is possible to read out the orientation of one single electron, one time, and get an answer. It is still one of 2. 104 years later, in equipment that would have looked like magic to Gerlach, the beam still refuses to give a 3rd answer. So we have it on a plate now, literally, a beam of atoms asked a question with infinitely many possible answers, and every one of them said one of 2 things. And that would be strange enough. But the truly disorienting part of the Stern-Gerlach experiment is not what happens when you run it once. It is what happens when you run it twice. Take the apparatus from the last part and put a second one behind it. This is the experiment that turns a strange result into a different universe. And for a long time, it was something physicists only did on paper. A teaching device. A thought experiment used to walk students to the edge of a cliff. It has since been done for real, with metastable helium atoms and with trapped ions, and in several other systems, and it behaves exactly as the mathematics said it would. Here is the setup. First magnet, oriented vertically. The beam splits into 2. Take the upper beam, every atom in it has just been measured and found to be up along the vertical axis, and block the lower one completely so that nothing from it continues. What you now have is a beam of atoms that are all, unambiguously, up. You can check that. Send that beam through a second vertical magnet, and it does not split. Everything goes up again, 100%, no exceptions. The measurement is stable and repeatable, which is what you would expect, and what makes the next part so difficult. Now rotate the second magnet 90 degrees so that it sorts along the horizontal axis instead, left and right, rather than up and down. Classically, this is a null experiment. A magnet pointing straight up has no component along the horizontal direction. None. Zero. Exactly. A horizontal field gradient has nothing to grip. The atoms should sail through untouched and land in a single spot, undeflected. They split, left and right, in exactly equal numbers, 50-50, every time. Take a moment with that. These are atoms that have been measured. They are definitely up. And when you ask them a question about left and right, half of them say left and half say right, and there is no property of the individual atom that you could have measured beforehand to predict which. Now the third stage, which is where the floor gives way properly. Take the beam that came out on the left. Every atom in it has now been measured twice, found up along the vertical axis, then found left along the horizontal axis. Send it through a third magnet, oriented vertically again, back to the original question. It splits, half up, half down. The atoms were definitely up. You measured it, you verified it by repeating it. Then you asked about left and right, and in the act of answering that question, the atoms lost the answer to the first one. Not partially, completely. The vertical measurement is now a coin flip again, as though the first magnet had never been there. There is no way to arrange a hidden internal arrow that does this. That is the point I want to press on, because it is the difference between quantum mechanics being weird and quantum mechanics being a genuinely different description of what exists. If the electron had a real orientation, some definite direction in space that measurements merely revealed crudely, then measuring along a new axis would give you additional information about that direction, not destroy the information you already had. You would be triangulating. Instead, you are erasing. The formal name for this is non-commuting observables. It means that the order in which you ask the questions changes the answers you get. Measure vertical, then horizontal, and you get one thing. Measure horizontal, then vertical, and you get another. In ordinary experience, the order of two measurements is irrelevant. You can weigh a suitcase, then measure it, or measure it, then weigh it, and the answers are the same both ways. For the orientation of an electron, order is everything, and every pair of different axes has this property. The underlying reason is deeper than any statement about electrons in particular. It comes from the structure of rotations themselves. Rotations in 3 dimensions do not commute. Turn a book 90 degrees about one axis and then 90 about another. Then do the same 2 turns in the opposite order, and the book ends up in 2 different orientations. Try it with something on the bed beside you. The order matters for ordinary objects too. What quantum mechanics does is take that fact about the geometry of rotations and make it a fact about knowledge. Because the rotations do not commute, the corresponding measurable quantities cannot be simultaneously sharp. There is a version of the uncertainty principle for this, and it is not the position and momentum one people usually quote. It is a relation between the different components of angular momentum. Sharpen your knowledge of the electron's orientation along one axis, and you necessarily blur it along the other 2. Make it perfectly sharp along one, which is what a Stern-Gerlach measurement does, and the other 2 become completely undetermined. Here is a piece of geometry that makes it vivid, and that is usually skipped in first explanations because it is uncomfortable. The total magnitude of an electron's spin angular momentum is not 1/2 in the natural units. It is the square root of 3/4, about 0.866. But the largest value you can ever measure along any axis is 1/2, 0.5. So the vector, if we insist on calling it a vector, is always longer than its own maximum possible projection onto any direction, which means it can never point along the axis you are measuring, not even when you have just measured it and got the maximum possible answer. There is always some of it left over, unaccounted for, in the directions you did not ask about, and the amount left over is exactly the amount that has to be indeterminate. That is not a limitation of the apparatus. There is no better magnet. It is a statement about what kind of thing the electron's angular momentum is. And the statement is, it is not an arrow in space. I said in the first part that the electron is not spinning. This is the sharper version of that claim. It is not that the electron is spinning in some way we cannot picture. It is that the electron does not have a rotation axis. There is no direction associated with it, waiting to be discovered, being approximated by our clumsy measurements. Ask along vertical, and you get one of two answers. Ask along horizontal, and you get one of two answers. Ask along an axis tilted at some arbitrary angle, and you get one of two answers, the same two magnitudes as before, with probabilities that depend on the angle. Every axis gives two. There is no axis that gives a special or true answer, and each answer destroys the last. There is a useful way to feel the shape of this. Imagine you had an object that, whichever way you looked at it, appeared to be exactly 1 meter long, not 1 meter when viewed end-on, and shorter when viewed at an angle, but 1 meter from every direction, always, with no exceptions and no foreshortening. You would fairly quickly conclude that it is not an object with a length and an orientation. Something about the way you are conceiving of it is wrong. That is the situation with the electron's angular momentum. The magnitude you measure is the same in every direction you choose, and the only thing that varies is the sign. Whatever it is, its relationship to the space you are measuring in is not the relationship a rod has to the room it is lying in. Pauli's phrase is starting to look less like evasion, isn't it? A classically non-describable two-valuedness. Two values, along whatever axis you choose, with no underlying direction generating them. He wrote that in 1925, before the sequential experiment had been analyzed, before anyone had a formalism to express it, and it is still, a century later, the most precise short description available. There is one more thing about the sequential experiment that matters enormously, and it is easy to miss. If you split the beam with the first magnet, but do not record which path each atom took, if you let the two beams separate, and then bring them carefully back together, with no measurement made anywhere, the original state is restored perfectly. The atoms come out the far side exactly as they went in. The splitting alone does not destroy anything. Only the recording does. Which means the erasure we have been talking about is not caused by the magnetic field roughing up the atoms. It is caused by information becoming available. That is a very strange sentence to have to write about a piece of laboratory equipment, and it is one of the reasons this experiment sits at the foundation of how we think about measurement. It is also, incidentally, the reason quantum cryptography works. If you encode information in the orientation of particles along axes that your recipient knows, and an eavesdropper does not, then anyone who measures along the wrong axis destroys what they were trying to read and leaves a statistical fingerprint of having tried. The security is not clever mathematics. It is this: the fact that asking the wrong question erases the answer. So by 1925, physics had a property with two values along every axis, no underlying direction, a magnetic moment twice as large as any rotation could produce, and a name that described a motion that was not occurring. What it did not have was any way to write it down. Let us step back for a moment and put the pieces on the table together, because we are halfway through, and the evidence has been arriving from 4 different directions. From Berlin, a cylinder of iron that rotates when you magnetize it, telling us that magnetism carries genuine mechanical angular momentum, and telling us, once the measurements were done properly, that whatever carries it produces twice as much magnetism per unit of rotation as any orbiting charge can. From Leiden, spectral lines that split in a magnetic field into patterns requiring half-integer quantum numbers, which the entire architecture of quantum theory said were not allowed to exist. From Frankfurt, a beam of atoms asked about direction, and answering with exactly two values, sharply, with nothing in between. And from the sequential version of that experiment, the discovery that the two answers along one axis are annihilated by asking about another. 4 results, 1 missing property, and a picture, a small ball of charge turning on its axis, that had been shown to require surface speeds more than 100 times the speed of light in an object that, as far as anyone could measure, has no surface at all. What physics did not have, in 1926, was any way to write the property down. That may sound like a small technical complaint. It is not. In quantum mechanics, the way you write something down is the theory. The whole apparatus is built on a single object, the wave function, which contains everything that can be known about a system, and on an equation that says how that object changes with time. That equation had just arrived. Erwin Schrödinger published it in 1926, and it was, for a few months, the most exciting thing in physics. It described quantum objects as evolving distributions of probability. Feed it a hydrogen atom, and out come the energy levels, the right ones, in the right places, from a single elegant piece of mathematics, rather than from Bohr's collection of rules and postulates. Everything the old quantum theory had asserted, the Schrödinger equation derived. Everything except this. The wave function as Schrödinger conceived it assigns a single complex number to each point in space. One number, one value per location. That is what a wave function is, a field of amplitudes. And there is nowhere in that structure to put a two-valuedness. You cannot squeeze a property with two states into a single number per point, any more than you can record a stereo recording on a single track. So Pauli did the crude, obvious, correct thing. In 1927, he wrote down a modified equation in which the wave function is not one function, but two, stacked together, a pair of complex numbers at every point instead of one. Two components, because the property has two values. It is not subtle. He did it by hand, motivated entirely by the experimental necessity, and the mathematics that resulted worked. The Pauli equation predicted the anomalous Zeeman patterns correctly. It handled the magnetic moment. It fitted. It is worth understanding what those two numbers actually do, because it is more elegant than the phrase two components suggests. The pair is not a list of two separate facts. It is a single state, and the two numbers together encode the answer to every possible orientation question at once. Give me the pair, and I can compute for you the probability of getting up along the vertical axis, and along the horizontal, and along any axis tilted at any angle you care to name. All of it is in there, in two complex numbers. That is why a two-valued property does not need an infinite list of directions attached to it. Two numbers are enough to specify the whole pattern of answers to infinitely many questions. And the way those two numbers change when you rotate your point of view is where the mathematics gets its teeth. Pauli wrote down 3 small arrays of numbers. They are still called the Pauli matrices, and any physics student meets them in their second year, that describe how the pair transforms for rotation about each of the 3 axes. Those 3 objects have exactly the property we saw on the plate in the last part. They do not commute. Apply them in a different order and you get a different result, and the specific way in which they fail to commute reproduces, precisely, the erasure that happens in a sequential Stern-Gerlach experiment. The strangeness that had been sitting on a piece of glass in Frankfurt turned out to be an algebraic fact about three little arrays of numbers. There is a picture that goes with this, and it is worth having, because it is the picture most people carry, and it is subtly, instructively wrong. You can map every possible state of the pair onto a point on the surface of a sphere. It is called the block sphere, and it looks exactly like a direction in space. North pole means up, south pole means down. The equator holds the states that are equally likely to give either answer. Physicists draw it constantly. It makes spin look, at last, like an arrow. Keep that sphere in your mind, because we are going to come back to it. And when we do, the way the map works is going to turn out to be the whole secret of this episode. The correspondence between the sphere and the states is not one-to-one. Two different states of the pair map onto the same point on the sphere. The picture is a shadow, and it is a shadow that has lost exactly one piece of information, and that missing piece is the strangest thing about matter. But there is something worth noticing about that pair of numbers, and it is the reason I have brought you here, rather than skipping to Dirac. A stacked pair of complex numbers, which transforms in a particular way when you rotate your coordinate system, is not just a list. It is a specific mathematical object with its own name and its own strange properties, and it had already been invented. It was called a spinor, and it had been introduced in 1913 by the French mathematician Élie Cartan, working on the representation theory of the rotation group. Cartan was not thinking about electrons. Nobody had measured any of the four results we just listed. Three of them had not happened yet. He was doing pure mathematics, asking, in the abstract, what kinds of objects can exist that transform sensibly under rotations? Vectors are the familiar answer, arrows which rotate the way you expect. Cartan found that there is another family of objects that also transform consistently under rotations, but differently and more strangely, and he described them because they were there. They sat on the shelf for 13 years. Then physics reached for something to hold a two-valued property and found that the right object had been sitting there the whole time, fully worked out, waiting. I do not want to make this sound mystical, because it is not. Mathematicians explore the space of possible structures fairly systematically, and physics has been drawing on that stock for centuries. Riemann built the geometry of curved space 60 years before Einstein needed it. Group theory was developed for the study of equations and turned out to describe the taxonomy of particles. This happens often enough that Eugene Wigner wrote a famous essay about how unreasonably effective mathematics is at describing the physical world, and nobody has satisfactorily explained it. But there is something particularly pointed about this case. Pauli reached for the two-component object because he needed two values. What he had actually picked up was a thing with a property he had not asked for and did not yet know about, a property so alien that when it was finally understood, it explained not only the two-valuedness, but also the exclusion principle, the periodic table, and the solidity of matter. He had picked up an object that does not come back when you turn it all the way around. Nobody realized that yet. In 1927, the spinor was a piece of bookkeeping, an ugly patch on a beautiful equation, adopted because it worked, and disliked because it was ad hoc. Pauli himself regarded it as provisional. He had bolted a two-valued index onto the wave function by hand, and he knew perfectly well that bolting things on by hand is what you do when you do not understand something. 1 year later, a 25-year-old in Cambridge would derive the same object from first principles, without trying to, while working on a problem that had nothing to do with magnetism, spectra, or iron cylinders on threads. And that derivation would produce the factor of 2. Paul Dirac had a different problem, and it had nothing to do with magnetism. His problem was that the Schrödinger equation is not compatible with special relativity. This is not a philosophical objection, it is structural. Special relativity insists that space and time enter the laws of physics on the same footing. That you cannot write a fundamental equation that treats time differently from the three directions of space and expect it to hold in every frame of reference. The Schrödinger equation does exactly that. It has a first derivative in time and a second derivative in space. It is lopsided. It works beautifully for electrons moving slowly, and it fails for electrons moving fast, and electrons in the inner shells of heavy atoms move very fast indeed. Several people had tried to fix it. The obvious approach is to make the equations second order in time as well, matching the second order treatment of space. That gives you what is now called the Klein-Gordon equation, and it has problems. It produces probabilities that can come out negative, which is meaningless. Dirac attacked it from the other end. Instead of raising time to match space, he tried to lower space to match time, to write an equation that is first order in space as well as first order in time. That sounds harmless. It is not. The relationship between energy, momentum, and mass in relativity involves squares. The famous expression, where energy squared equals momentum squared times the speed of light squared plus mass squared times the speed of light to the fourth. To make a first-order equation, you have to take a square root of that expression, and you cannot take the square root of a sum of squares and get anything sensible using ordinary numbers, unless the coefficients are not ordinary numbers. Dirac's insight in the winter of 1927 and 1928 was to allow the coefficients in his equation to be objects that do not commute, objects where the order of multiplication matters. With that freedom, the square root can be taken. But it can only be taken if those objects satisfy a specific set of relations, and the smallest mathematical objects that satisfy those relations are 4 by 4 arrays, which means the wave function they act on cannot be a single number. It has to have 4 components. Read that again, because this is the moment. Dirac was not trying to describe magnetism. He was not trying to explain the anomalous Zeeman effect, or Einstein's iron cylinder, or the 2 spots in Frankfurt. He was trying to make quantum mechanics consistent with relativity, and the only way the mathematics would close was if the electron's wave function had multiple components that mix into one another under rotations. He had derived spinors, not adopted them, not bolted them on, derived them from the single requirement that quantum mechanics respect the geometry of space-time. And when he worked out what his 4-component wave function does in a magnetic field, the electron's magnetic moment came out. He did not put it in. There is no term in the Dirac equation that says the electron is magnetic. The magnetism emerges from the structure, and the strength that emerges corresponds to a gyromagnetic factor of exactly 2. 2. The number that had been wrong in Einstein's cylinder since 1915. The number that made the anomalous Zeeman patterns come out. The factor that no distribution of rotating charge could produce, that had sat unexplained for 13 years while people measured it more and more carefully and got the same impossible answer. That number fell out of an equation written by someone who was thinking about relativity and had, by his own account, no idea it was coming. That is what physicists mean when they say the Dirac equation is beautiful, not that it is short, although it is, that it was asked 1 question and answered 3. It answered a 4th as well, quietly. Remember the fine structure of hydrogen, the very small splitting of hydrogen's spectral lines that had tormented Kronig and then Uhlenbeck and Gaudsmit, and that had needed Thomas's relativistic correction applied by hand to come out right. The Dirac equation produces the fine structure directly, correct spacing, no corrections needed, no factor of 1/2 inserted afterwards. Thomas' precession is not added to the Dirac equation. It is already inside it, because the equation was built to respect relativity from the beginning, and Thomas' precession is nothing but relativity applied to a curved path. 3 separate patches, each invented to rescue a broken picture, all dissolved into a single equation that needed none of them. By the late 1940s, when experiments got good enough to find the tiny places where even the Dirac equation is not quite right, the Lamb shift, measured in 1947, a minuscule displacement of 2 hydrogen levels the equation says should be identical, those discrepancies became the seeds of quantum electrodynamics, the theory that would eventually predict the electron's magnetism to 12 decimal places. Every stage of that story runs through the property we still, misleadingly, call spin. The third answer was even less requested than the second. Dirac's equation has 4 components, and 2 of them describe the two-valuedness we have been chasing. The other 2 describe something with the same mass and the opposite charge. Dirac spent a long time trying to interpret those extra solutions and eventually concluded, reluctantly, that they described a new particle, an anti-electron, identical to the electron in every way except with a positive charge instead of a negative one. He predicted it in 1931. Carl Anderson found it in cosmic ray tracks in 1932 and called it the positron. Dirac received the Nobel Prize in 1933, at 31 years old. It is worth pausing on how reluctant that prediction was. Dirac's first attempt to make sense of the extra solutions was to suggest they described the proton, which was the only positively charged particle anyone knew about, an idea that failed immediately, since the proton is nearly 2,000 times heavier than the electron, and the equation insisted the 2 masses be identical. Only when that failed did he accept that his equation was describing something nobody had ever seen. He did not propose antimatter because he found the idea appealing. He proposed it because he had run out of ways to avoid it. So the same equation that finally explained the factor of 2 also predicted antimatter, and predicted it because the mathematics of taking that square root would not permit anything less. Both results came from the same source, the insistence that a quantum wave function transform correctly under the geometry of space-time. There is a detail in this that I find quietly moving, and it concerns how Dirac worked. He was famously silent. Colleagues at Cambridge joked about a unit of measurement called the Dirac, defined as 1 word per hour. He did not argue his way to results in seminars. He sat with the mathematics until it told him something, and he trusted what it told him, even when it was uncomfortable, which is exactly the methodological instinct Pauli had displayed by refusing to draw a picture of his two-valuedness. 2 very different personalities arrived at the same discipline. Take the structure seriously, and do not force it to look like something familiar. That discipline is the reason both of them succeeded where better-known physicists, with better physical intuition, failed. Everybody else was trying to build a model of the electron. Pauli and Dirac were trying to find out what the equations would tolerate. The electron turned out to be a thing you can only reach the second way. Now, I have to be careful here, because there is a version of this story that overclaims, and you will meet it often. The overclaim is that Dirac's equation proves the electron must have a magnetic moment of exactly 2, that this is a deep necessity of relativity, and that spin is therefore a purely relativistic effect. That is not quite right. It is possible to write down relativistic equations for particles with other values, and it is possible to obtain spin in non-relativistic quantum mechanics if you are willing to put in the right structure by hand, as Pauli did. What the Dirac equation does is something slightly weaker and, to my mind, more interesting. It shows that if you want the simplest relativistic description of a particle of a given mass and charge, the object you are forced to use is a spinor, and a spinor comes with a two-valuedness and a magnetic factor of 2 attached. Spin is not derived from relativity. It is the cheapest thing relativity will sell you. There is also the small matter of the word exactly. The Dirac value is 2. The measured value is not quite 2. It is 2.00231930,436, and so on. And the difference, that trailing 0.23%, was one of the great scandals of the 1940s and one of the great triumphs of the 1950s. The explanation is that the electron is never alone. The space around it is not empty, it is a quantum field, and that field is constantly producing and reabsorbing virtual particles that interact with the electron and slightly modify its magnetism. Julian Schwinger calculated the leading correction in 1948 and found that it is the fine structure constant divided by 2 pi, a number close to 0.00116, which accounts for nearly the entire discrepancy on its own. He was so pleased with it that he had the expression carved on his gravestone. We will come back to that number at the end, because it has since been pushed to a precision that is difficult to describe without sounding like exaggeration. But first there is the thing Dirac had picked up without noticing, the same thing Pauli picked up in 1927, that Cartan had left on a shelf in 1913, a spinor. And a spinor has a property that nothing you have ever held in your hands possesses. Turn it all the way around, and it does not come back. If there is anything in your reach, a mug, a glass of water, a phone, a book, pick it up now and hold it flat on your open palm, upright, as though you were carrying a drink across a room. Keep it level. Now rotate it, keeping your palm underneath it, turning it in a full circle. Not by moving your feet, by turning your hand and your arm. Take it round the outside first, then bring it in under your armpit, and keep going until it has completed one full turn. Look at your arm. Your elbow is up somewhere near your ear, your shoulder is twisted, and everything about the position says stop. One full turn, 360 degrees. The thing you did to it, exactly a whole circle, and you are not back where you started. The mug is upright, at the same place, facing the same way, entirely unchanged. Your arm is not. Now do the thing that feels wrong. Do not unwind. Keep going in the same direction. Take the mug up and over the top, past your shoulder, round again, a second complete turn, and watch what happens to your arm as it comes round. It untwists. At the end of the second full circle, your arm is hanging comfortably by your side, the mug is still upright, and nothing anywhere is under tension. 2 turns bring you home, 1 turn does not. And you can keep doing this forever, going the same way, and your arm will alternate between twisted and free, and it will never get tangled beyond recovery. That is not a trick. That is a real property of the geometry of rotations in 3-dimensional space, and it has a proper name. Physicists call it the belt trick, or the plate trick, or Dirac's string trick, because Dirac used it to explain exactly the thing I am about to tell you. There is a cleaner version if you want to picture it. Imagine a cube sitting in the middle of a room, connected to the 4 walls by a handful of loose ribbons. Rotate the cube through 1 full turn. The cube is back where it started. The ribbons are twisted. Rotate it through a second full turn in the same direction, and the ribbons, remarkably, can be untangled without moving the cube at all. You can do this any number of times, with any number of ribbons, and the system never gets permanently knotted. The tangle after 1 turn is real. The tangle after 2 turns is an illusion that can always be combed out. What this is telling you is that a rotation of 360 degrees, when you keep track of the object's connection to everything around it, is not the same as doing nothing. Only 720 degrees is the same as doing nothing. For ordinary objects, this is a curiosity. Nobody keeps track of the twist in the ribbons. When you turn a book all the way around, the book is back where it was, and that is the end of the story. For an electron, it is not the end of the story. It is the story. Rotate an electron's state through 360 degrees, and the wave function does not come back to itself. It comes back to minus itself. Every number in it flips sign. Only after a second full turn, 720 degrees, does the state return to what it was. This is the double cover. It is the property Cartan found in his spinors in 1913 without knowing what it was for, and it is the property Pauli and Dirac picked up without asking for it. And it is not a mathematical convention or an artifact of how we choose to write things down. It has been measured. Here is the difficulty in measuring it. The overall sign of a wave function is not observable on its own. Multiply everything by -1, and every prediction the theory makes stays identical. So you cannot detect the sign flip by rotating an electron and then looking at it, because there is nothing to see. The information is real and completely hidden, unless you rotate only half of it. In 1975, Helmut Rauch and his colleagues in Vienna, and independently, Samuel Werner and his colleagues in the United States, did exactly that with neutrons. The neutron is also a spin 1/2 particle. It should have the same double cover property as the electron, and it has the enormous practical advantage that you can build an interferometer for it. The device is a single perfect crystal of silicon, cut so that a beam of neutrons entering it splits into two paths that travel apart for a few centimeters and are then brought back together. Where they recombine, they interfere, and you count how many neutrons arrive. If the two paths are identical, the beams arrive in phase and reinforce each other, and you count a lot of neutrons. Then you put a magnetic field on one path only. A magnetic field makes a neutron's spin state precess. It rotates it by an amount you control precisely by adjusting the field strength. So now 1/2 of the beam has been rotated by some angle, and the other half has not, and the two halves are brought back together and asked to interfere. Turn the field up slowly and watch the count. If the rotated half needed only 360 degrees to come back to itself, the interference pattern would repeat every 360 degrees of precession. It does not. The count falls to a minimum at 360 degrees. The two halves of the beam are exactly out of phase and cancelling, and rises back to a maximum only at 720. A neutron rotated once all the way around destructively interferes with a neutron that was not rotated at all. They cancel. The same particle, from the same source, split moments earlier. One of them turned through a complete circle and put back, and the two of them annihilate each other's contribution. Only after two complete turns does the neutron agree with itself again. That experiment has been repeated and refined for 50 years, and the answer does not move. 720 degrees, not 360. There is a wrinkle in this that is worth knowing, because it shows how strange the double cover really is. In 3 dimensions of space, the rotation group has exactly 2 covers, the ordinary one and the double one, which is why nature offers exactly 2 kinds of particle, the ones that come back after 1 turn and the ones that need 2. But if you confine particles to a flat 2-dimensional surface, the mathematics changes completely. In 2 dimensions, the covering structure is infinite, and particles can in principle pick up any phase at all when you take one around another. Those particles are called anyons, and they are not hypothetical. They have been observed in the strange quantum states that form when electrons are confined to an extremely thin layer at very low temperature in a strong magnetic field, and they are the leading candidate for building a quantum computer that is naturally protected from errors. The reason our universe only gives us fermions and bosons is that we live in 3 spatial dimensions and not 2. There is a consequence of the double cover that I want to plant now, because it is going to become the last movement of tonight's story. Think about what it means to swap 2 identical particles, to pick up 2 electrons and exchange their positions. If you follow the paths carefully, the operation of exchanging 2 particles is topologically the same as rotating one of them through 360 degrees relative to the other. They are the same maneuver described 2 ways, and we have just established what a 360-degree rotation does to a spinor. It multiplies it by -1. So exchanging two electrons must multiply their combined state by -1. That minus sign is not an extra assumption. It is the double cover, showing up in a completely different context, and it is going to turn out to be the reason the floor holds you up. Hold on to it. Now I want to connect this back to the sphere I asked you to hold on to 2 parts ago. Remember the block sphere, the picture where every possible state of the electron's 2 components maps onto a point on a globe, north pole for up, south pole for down, equator for the undecided states. The reason that picture is a shadow is exactly this. Going once around a great circle on the sphere brings the point back to where it started. It does not bring the state back. The sphere is the space of directions. The state lives somewhere above it, in a space that wraps around twice for every once the sphere does. That is what mathematicians mean when they say the rotation group has a double cover. Ordinary directions in space form one structure. Spinors live in a structure that maps onto it 2 to 1. Every direction in your room corresponds to 2 distinct electron states, and there is no way to choose between them consistently. Which brings us, finally, to the question this episode is named for. We have established that the electron is not spinning. It has no size, so there is nothing to rotate. Its angular momentum is fixed at a value that cannot be changed. Measuring its direction along any axis gives one of exactly 2 answers and destroys the answers along the other axes. And now this. Rotating it all the way around does not put it back. An object that must be turned twice to return to itself is not an object in the ordinary sense. It is not a ball, or a top, or a wheel, or anything you could hold, because everything you can hold comes back after 1 turn. Whatever the electron is, its relationship to the space around it is not the relationship a thing has to a room. Every classical picture is now gone. There is no ball, there is no axis, there is no rotation, there is no orientation. What is left? Something is left. It is precise, it is beautiful, and it has been sitting in the mathematics since 1918, discovered by a woman working in Göttingen without a salary because the university would not pay a woman to teach. We are ready for the answer. To answer the question we started with, we have to stop thinking about rotation and start thinking about momentum, ordinary momentum, the kind a thrown ball has. In 1918, in Göttingen, a mathematician named Emmy Noether proved a theorem that is arguably the single most important structural result in physics. She was working without pay because the university would not appoint a woman to a salaried position, and lecturing under David Hilbert's name because she was not permitted to hold a lectureship of her own. Hilbert reportedly told the faculty senate that he did not see what her being a woman had to do with anything, since the Senate was not a bathhouse. What she proved is this. Every continuous symmetry of the laws of motion corresponds to a conserved quantity, and the correspondence is exact and mechanical. You can compute one from the other. If the laws of physics are the same here as they are 1 meter to the left, if nothing about the rules depends on where you are, then linear momentum is conserved. That is the whole reason momentum is conserved. Not because objects are stubborn, not because of anything about the objects at all, but because space does not care where you are. If the laws are the same today as tomorrow, if the rules do not depend on when you are, then energy is conserved. And if the laws are the same whichever way you are facing, if nothing about physics depends on your orientation, then angular momentum is conserved. That last one is the ledger from the very first part of this episode. The lecturer on the swivel stool, the bicycle wheel, the iron cylinder turning on its thread. The books balance not because rotating objects have some innate tendency to keep rotating, but because the universe has no preferred direction, and Noether's theorem converts that indifference into a conservation law. Now hold that thought and consider the quantum version. In quantum mechanics, the quantities that Noether pairs together become what are called conjugate variables. Position and linear momentum are the classic pair. They are two descriptions of the same state. You can write a particle's wave function as a distribution over positions or as a distribution over momenta, and the two are mathematically equivalent, each derivable from the other. And because they are two views of the same object, sharpening one blurs the other. That is Heisenberg's uncertainty principle. A particle with a perfectly definite momentum has a completely indefinite position. It is not anywhere in particular, not hiding somewhere we have not looked. Nowhere in particular is its actual condition. So here is the question that unlocks everything. If position is the conjugate partner of linear momentum, what is the conjugate partner of angular momentum? The answer is angular position, orientation, which way the thing is facing. And now run the same logic through. A particle with a perfectly definite angular momentum must have a completely indefinite orientation. That is the answer. That is what spin is. The electron does not have an orientation that we keep failing to measure. It does not have a hidden axis that our clumsy magnets can only sample crudely. It has no orientation at all, and that is not a defect, or a mystery, or a limit on our knowledge. It is the precise, necessary, mathematical price of having an angular momentum that is exactly, unchangeably, 1/2. The two facts are the same fact. The electron's angular momentum can be perfectly sharp only because its orientation is perfectly absent. Just as a particle in a state of perfectly definite momentum is nowhere in particular, a particle in a state of perfectly definite angular momentum is facing nowhere in particular. So the question we have been circling for the whole episode, if the electron is not spinning, what is doing the spinning? Turns out to be malformed. There is nothing doing the spinning. What the electron has is a rotational degree of freedom, a way in which it can be acted on by rotations, a set of states that transform into one another when you turn your point of view. Noether's theorem does not require anything to be turning. It requires only that the laws be indifferent to direction and that the system have some way of responding to rotation. Give it that, and a conserved quantity appears automatically, whether or not anything is moving. That is the whole trick. Angular momentum is not made of rotation. Angular momentum is what rotational symmetry produces. Rotation is one way to have a rotational degree of freedom. It is not the only way, and for an electron, it is not the way. There is a piece of evidence for this that has been sitting in the arithmetic since the 1920s, and once you see it, you cannot unsee it. Orbital angular momentum, the real kind, the kind that comes from an electron genuinely circulating around a nucleus, from a planet going round a star, from anything actually moving in a curve, is always a whole number of units. 1, 2, 3, never a half. And there is a clean reason why. Real motion around a loop has to come back to itself after one full circuit, and that requirement forces the possible values to be whole numbers. Spin is never a whole number for the electron. It is 1/2. Always 1/2. Exactly 1/2. And it cannot be anything else. That difference is not a detail. The half integer values are the fingerprint of something that does not have to come back after one circuit, of a state that is permitted to return, to minus itself after a full turn. Whole numbers are what you get from things that go around. Halves are what you get from things that do not. The arithmetic was announcing the double cover 20 years before anyone worked out what it meant, and it was announcing it in Landé's empirical formula, in a table of spectral line spacings, in 1921. I want to sit here for a moment, because this is the part of the story I find genuinely moving, and it is worth letting it settle before we move on. We spent the first half of tonight watching a picture fail, a ball of charge, turning. It failed on speed. You would need surface velocities more than 100 times the speed of light. It failed on size. The object has no measurable size at all, and you cannot spin a point. It failed on direction, measure along one axis, and the answers along the others evaporate. It failed on rotation itself, turn the thing all the way around, and it does not come back. Every one of those failures is the same failure, seen from a different angle. They are all consequences of trying to give the electron an orientation, and the electron does not have one, because if it had one, its angular momentum could not be exact. This is not physics conceding defeat. It is physics giving a complete answer to a question that was asked slightly wrong. The universe was never obliged to build angular momentum out of things going round in circles. It was obliged only to conserve the quantity that rotational symmetry generates, and it has done so, scrupulously, in every experiment ever performed, including in a cylinder of soft iron hanging from a thread in Berlin in 1915, which turned by a fraction of a degree because a very large number of electrons that were facing nowhere in particular changed which of two values they were reporting. The ledger balanced. Nothing turned. And notice what has happened to that ledger over the course of this episode. In the first part, it looked like bookkeeping, about spinning objects, a rule for keeping track of wheels and stools and cylinders, the sort of thing that exists because rotating things are stubborn. It is not that. The ledger is prior to the objects. It exists because space has no favorite direction, and it would exist in a universe containing nothing that rotates at all. The wheel does not create the conservation law. The conservation law was already there, and the wheel is one of the things obliged to obey it. So is a piece of iron. So is an electron that has no orientation, no size, and no motion, because obedience to that law never required motion in the first place. That is the reversal I have been walking you toward all night. We began with a demonstration that seemed to explain angular momentum by showing you something turning. The turning was never the explanation, the symmetry was. There is one more layer worth adding, because it is the cleanest statement anyone has produced. In modern physics, we do not really define particles by what they are made of. We define them by how they respond to the symmetries of space-time, to translations, to rotations, to the changes of viewpoint permitted by relativity. Eugene Wigner worked out the complete classification in 1939, and the result is that a particle is fully specified by exactly two numbers, its mass and its spin. Not its mass and its size, not its mass and its shape, its mass and its spin. Those two labels tell you everything about what kind of thing it is, and every other property, charge, color, flavor, is additional decoration on top, which means spin is not a property that electrons happen to have, in the way that a car happens to be blue. It is half of the definition of being an electron. Change it, and you are no longer talking about an electron. It is as fundamental as mass, and it was hiding inside a factor of 2 in a magnetism measurement that Einstein misread as a success. So that is the answer, and it is honest, and it holds together. The electron has a rotational degree of freedom, no orientation, and a conserved quantity that follows from the symmetry of space itself. Most physicists would stop there and tell you that asking what is actually circulating is a category error inherited from a bad name. Not all of them, though, and the ones who disagree have a calculation. I have just spent a part of this episode telling you that nothing is circulating, and I meant it. But I would be giving you a tidier story than the one physics actually has if I stopped there, because there is a serious minority position that says something is circulating after all, and it is not held by cranks. The argument goes back to a Dutch physicist named Frederik Belinfante in 1939, and it was revived and sharpened by Hans Ohanian, the author of a widely used quantum mechanics textbook, in a paper in the American Journal of Physics in 1986 with the pleasingly blunt title, "What is Spin?" Here is the idea, and it turns on a distinction that is easy to slide past. The electron is point-like. That is well established. No experiment has found any structure, and the bounds are extraordinarily tight. But the electron's field is not point-like. In quantum field theory, an electron is an excitation of a field that extends through space, and although the charge and mass are concentrated at a point, the field around that point is a real, extended thing, with real energy and real momentum distributed through it. So Ohanian asked the obvious question. Take the Dirac field around an electron. Compute, using the entirely standard expressions of the theory, how energy flows in that field. Compute how charge flows in it. Do not assume anything about spin, just work out the flows. The flows circulate, then integrate. Add up the angular momentum carried by that circulating energy across the whole field, and you get 1/2 of the reduced Planck constant. Exactly. Add up the magnetic moment produced by the circulating charge, and you get the Dirac value, the factor of 2, the number that broke Einstein's experiment. Neither result is inserted. Both come out of the field. On this reading, spin genuinely is angular momentum in the ordinary mechanical sense. It just does not live in the particle. It lives in the field around the particle, spread over a region set by the electron's reduced Compton wavelength, about 3.8 times 10 to the minus 13 meters. That is small, roughly 100 times the size of an atomic nucleus, but it is emphatically not zero, and when you work out how fast the energy is circulating over that distance, the answer is comfortably below the speed of light. Ohanian's conclusion is that the electron's spin is entirely analogous to the angular momentum carried by a circularly polarized light wave. And that is a completely unmysterious thing. A beam of circularly polarized light really does carry angular momentum. Richard Beth measured it in 1936 by suspending a quartz plate on a fiber and detecting the torque as the light passed through. Today, the same effect is used routinely in optical tweezers to rotate microscopic beads and even living cells with nothing but a laser. So one reading of tonight's story is, the electron is a point with no orientation, and spin is a label describing how its state responds to rotations. Another reading is, the electron is a point wrapped in a field, and the field is genuinely swirling, and spin is the angular momentum of that swirl. Both readings make identical predictions. Every experiment ever performed is consistent with both, and that is worth saying clearly rather than pretending the matter is settled. A century after the property was discovered, physicists have not agreed on what it is, and the disagreement has no experimental consequence whatsoever. It is a disagreement about which picture to carry in your head while doing identical calculations. There are real objections to the field circulation view, and they are technical. The split of angular momentum into a spin part and an orbital part turns out to be ambiguous in theories with gauge fields, in a way that becomes acute in the strong nuclear force. That ambiguity is the technical heart of what is called the proton spin crisis. The proton is spin 1/2, made of 3 quarks that are each spin 1/2. And for decades, the assumption was that the quark spins simply added up to the protons. In 1987, the European muon collaboration measured how the spin is distributed and found that the quarks account for only about 30% of it. The rest is carried by gluons and by orbital motion inside the proton, and the accounting still does not close cleanly today. Even where spin is definitely composite, made of things we can name, we cannot say exactly where it lives. So the mystery does not shrink as you go up in scale. It gets larger. While we are being honest about the alternatives, it is worth saying what does not work, because a great deal of effort has gone into trying. Classical models of the electron as a small rotating ring, shell or vortex of charge have been proposed steadily for over a century. Alfred Parson published one in the same year Einstein hung his cylinder on a thread, and they keep being revived. They fail on 3 counts. and the three failures are the same ones we have already walked through. The required surface speed exceeds the speed of light for any size compatible with what experiments allow. A ball of pure negative charge blows itself apart unless you add a binding force nobody can name, which is a problem that occupied Poincaré and was never solved. And crucially, no such model has ever reproduced the 720-degree behavior, which is not a theoretical inference, but a measured fact sitting in 50 years of neutron interferometry data. There is also a numerological cul-de-sac worth flagging, because it circulates persistently. Lorentz's calculation gave a required surface speed of about 137 times the speed of light, and 137 is famously the reciprocal of the fine structure constant. People have built a great deal on that coincidence. It is not a coincidence, and it is not deep. The calculation involves the ratio of the electron's magnetic moment to its rest energy scale, and the fine structure constant is built into precisely that ratio. The number appears because it has to. It explains nothing about spin. And then there is the opposite error, which you meet in popular accounts constantly, the claim that spin is just mathematics, a bookkeeping index with no physical content. That is false, and the whole first half of tonight is the refutation. Spin exerts torque. It stores angular momentum that can be handed to a macroscopic object and made to turn it. It was measured mechanically, on a thread, in 1915, before anybody had the mathematics at all. Whatever spin is, it does work in the world. The honest position is the uncomfortable one in the middle. It is unambiguously real, unambiguously measured, and still without an agreed picture. And yet, and this is the thing that makes the whole subject so difficult to be comfortable with, this unresolved, unpicturable property is the most precisely measured quantity in the history of science. In 2023, Xing Fan, Thomas Myers, Bingjia Sukra, and Gerald Gabriels published a measurement of the electron's magnetic moment made with a single electron. 1. Held in a magnetic field of about 5 Tesla, in a trap cooled to around 50 thousandths of a degree above absolute zero, isolated well enough that they could watch it change its state one quantum at a time. The number they got for the ratio of the electron's magnetic moment to the natural unit is 1.00115965218059, with an uncertainty in the last 2 digits. That is a relative precision of 0.13 parts per trillion. It improved on a measurement that had stood for 14 years by a factor of a little over 2, and it makes the electron's magnetism the most precisely determined property of any elementary particle in existence. Now compare it to theory. Quantum electrodynamics predicts the same quantity by summing thousands of contributions, the Schwinger term first, then increasingly baroque corrections, out to the 5th order of the calculation. Prediction and measurement agree to roughly 1 part in a million. That is the most precisely verified prediction human beings have ever made about anything. It is the crown jewel of theoretical physics. It is the number people point to when they want to argue that we genuinely understand the microscopic world. And it is a number describing the strength of the magnetism of a thing that is not rotating, has no size, faces no direction, and does not come back when you turn it around. We can predict it to 12 decimal places. We cannot agree on what it is. Put your hand flat against something solid, the wall beside you, the frame of the bed, the surface of a table. Press. Nothing in that surface is touching your hand. I do not mean that poetically. The atoms in the wall and the atoms in your hand are, both of them, almost entirely empty. If you scaled a single atom up until its nucleus were the size of a marble, the nearest electron would be something like half a kilometer away, and everything in between would be nothing at all. The nucleus in the wall closest to your skin is, on its own scale, unimaginably far from you. Two clouds of near vacuum are approaching one another, and something is stopping them, and it is not contact, because there is nothing there to make contact with. There is a common answer to this, which is that the electrons in your hand repel the electrons in the wall because both are negatively charged. That is true, and it is not the main effect. Electric repulsion between two neutral objects falls off very quickly, because every negative charge is accompanied by a positive one, and the two very nearly cancel. If electrical repulsion were the whole story, matter would be far more compressible than it is. The thing that actually stops your hand is a prohibition, and the prohibition is the property we have spent this entire episode failing to picture. Here is how it works, and it comes straight out of the double cover. Remember what we established when you were rotating a mug on your palm. Exchanging two identical particles is topologically the same operation as rotating one of them through a full turn relative to the other, and a full turn multiplies a spinor by -1. So swapping two electrons multiplies their combined state by -1. Now ask, what happens if two electrons are in the same state, same place, same energy, same everything? Swap them. Since they are identical, and in identical states, nothing has changed, so the state must be the same as before. But the swap also multiplied it by -1, so the state must equal minus itself. There is only one number that equals minus itself: 0. Two electrons cannot occupy the same quantum state, because the mathematics assigns that possibility an amplitude of exactly 0. Not a small probability, not an unlikely arrangement. It does not exist as a possible configuration of the world. That is the Pauli exclusion principle, and Pauli stated it in 1925, before spin had a name, as a rule extracted from spectral evidence. The deep reason for it, that it follows from the same double cover that makes the neutron interfere destructively with itself after one turn, was not established until 1940, when Pauli published a paper in Physical Review titled "The Connection Between Spin and Statistics," developed with his assistant Marcus Fiers the year before. The theorem says that the universe divides all particles into two families, and the dividing line is the spin quantum number. Particles with half-integer spin, 1/2, 3/2, 5/2, are fermions. Their combined state changes sign when you swap two of them, so no two of them can ever be in the same state. Electrons, protons, and neutrons are all fermions. So is every particle that ordinary matter is made of. Particles with integer spin, 0, 1, 2, are bosons. Their combined state does not change sign under exchange, so they can pile into the same state without limit, and in fact they prefer to. Photons are bosons, so are gluons, and the Higgs. Two families, two completely opposite social behaviors, and the only thing that determines which family a particle belongs to is whether it comes back after one turn or needs two. Now watch what that prohibition builds. Start with an atom. Electrons want the lowest available energy, and if they could all have it, they would all sit in the innermost level, and every element in the universe would behave more or less identically. Exclusion stops them. Two electrons fill the first level, and the third has nowhere to go but up. 2, then 8, then 18, then 32. The shells fill in a fixed order, and the outermost shell of each atom determines how it bonds to its neighbors. That is chemistry. All of it. The reason carbon forms 4 bonds and can build molecules of unlimited complexity, the reason oxygen is desperate for 2 more electrons, the reason neon will not react with anything at all, every one of those facts is a statement about how far through filling a shell an element happens to be, and shells exist only because of exclusion. The periodic table on the classroom wall is a picture of the double cover. The rows are as long as they are because a spinor turned once around comes back as its own negative. Then keep going, because the same prohibition operates in bulk. Squeeze a solid, and you are trying to force its electrons into a smaller volume, which means forcing them into fewer available states. Exclusion will not permit them to share, so they are pushed into higher and higher energy states, and the energy cost of continuing to squeeze rises steeply. That resistance is called degeneracy pressure, and it has nothing to do with heat or motion or repulsion. It is the pure cost of the prohibition. It would be there at absolute zero, in a perfectly cold object, with nothing moving at all. Degeneracy pressure is what makes solids solid, and it does not stop at human scales. When a star like the Sun exhausts its fuel, gravity crushes the remnant inward, and nothing thermal can stop it, because the fire has gone out. What stops it is electron degeneracy pressure. A white dwarf star is roughly the mass of the Sun packed into the volume of the Earth, held up against its own gravity, permanently, by nothing but the fact that its electrons cannot share states. It can hold that pose for longer than the current age of the universe. There is a limit. Subrahmanyan Chandrasekhar worked it out as a 19-year-old on a ship from India to England in 1930, and found that above about 1.4 times the mass of the Sun, degeneracy pressure loses and the star collapses. Push past it, and the electrons are forced into the protons, and what remains is a neutron star, an object the width of a city, holding up an entire star's worth of mass, at the density of an atomic nucleus, supported by exactly the same prohibition applied to neutrons instead. And the bosons do the opposite, which is the cleanest proof that spin is what governs the difference. Cool a gas of atoms whose total spin comes out as a whole number, and instead of resisting one another, they collapse into a single shared quantum state, a Bose-Einstein condensate, first achieved in 1995 in a vapor of rubidium at 170 billionths of a degree above absolute zero. Liquid helium below about 2.2 Kelvin does something similar and becomes a superfluid, flowing without any viscosity at all, creeping up and over the walls of its container. Same universe, same forces. The only difference between matter that stacks and matter that merges is whether a full turn brings the thing back to itself. There is one more thing worth saying before we close, because it moves this out of the realm of stellar remnants and back into the room you are lying in. We do not merely understand this property, we use it. If you have ever had a magnetic resonance scan, a machine spent several minutes flipping the two valued states of the hydrogen nuclei in your body between their two allowed orientations and listening to the faint radio signal they gave off as they relaxed back. The image of your own soft tissue was assembled entirely out of a property nobody can picture. Read one flip at a time. If you have ever used a computer with a spinning hard disk, the head that read the data worked by giant magnetoresistance, an effect discovered in 1988, in which the electrical resistance of a stack of ultra-thin magnetic layers changes dramatically depending on how the two valued states in adjacent layers are aligned relative to one another. That discovery earned a Nobel Prize in 2007 and made the storage densities of the last 2 decades possible. Every photograph you kept, for years, was held in place by the orientation of something that faces no direction. And there is an entire field, spintronics, working to build devices that carry information in this property rather than in electric charge, because a state that only has 2 values and cannot be shared is, in some respects, a better place to keep a bit than a moving current is. So let me return to where we started. A lecturer sits on a stool and flips a bicycle wheel, and the stool turns and the ledger balances. A cylinder of iron hangs from a thread and rotates when you magnetize it, and the ledger balances, and nothing is turning. Electrons do not spin the way you think. They do not spin at all. There is no ball, no axis, no surface, no rotation, and no direction they are facing. What they have is a rotational degree of freedom and a conserved quantity that follows from the fact that space itself has no preferred direction. Wolfgang Pauli, refusing every picture anyone offered him, called it a classically non-describable two-valuedness in 1925, and 101 years later, that awkward, unlovely phrase is still the most accurate sentence anyone has written about it. And that unpicturable thing is holding you up right now. Not gravity. Gravity is pulling the other way. Not the solidity of the mattress, because the mattress is empty space. What is holding you is a prohibition that traces back through the spin statistics theorem, through the exchange of identical particles, to the fact that a certain kind of mathematical object needs to be turned around twice before it agrees with itself again. You are resting on the geometry of rotations. The most reliable experience any human being has, the ground being there, the floor holding, the world supporting your weight without being asked, rests on the least explicable property in physics. We can measure it to 14 significant figures. We can predict it to 12 decimal places, more precisely than we can predict anything else in the universe. We have known about it for 111 years, since a cylinder of iron turned on a thread in Berlin, and Einstein read the answer as agreement. And we still cannot say what it is. Thank you for spending this time with me, following one word, one badly chosen word from 1925, all the way down to the bottom of matter. If this is the kind of question you like to fall asleep to, a like or subscribe would mean a great deal, and it helps me keep making these. And remember, the next time you put your hand flat against a wall and feel it hold, nothing in there is touching you, and nothing in there is turning. Good night, and may you never look at the word spin the same way again.